Alright guys, so this is finally our first video on the lecture, right? So we're gonna take it where we left off last time, where last time we met in the classroom, right? So that is the last couple sections. Notice these papers I gave you, they have 8.7 and 8.2 because ultimately they're basically the same, right? So the 8.8, which would be applications of double integrals, its applications to volumes, right? But ultimately what we do in 8.7 is compute volumes, right? Given these double integrals, right? So before actually computing double integrals, right? So let's define a couple of terms right here, like iterated integrals. What do we mean by iterated integrals? Well, iterated means repeated, right? That's another way to say repeated. And you might have heard this term if you have taken a programming class, for example, iterations, right? When you do cycles, right? And these integrals are used to compute, to calculate volumes, average values, and we're gonna skip average values and total accumulations. We just have time to cover whatever they mean in this case, the volume. Okay, so, and in this case, as usual, we are going to consider the cases in which we have continuous functions, right? So otherwise we would have to define certain functions as piecewise functions, and then the problems will turn into very, very huge problems. But that's not the scope of this course, right? All right, before looking at the double integrals, let's look at partial integration. So partial integration is the analogous idea of partial differentiation, right? For example, if you have f of x, or let me just call it z equals x squared y cubed, right? We can take partial derivatives, right? A derivative of z with respect x, in this case 2x, and we hold y cubed constant, right? On the other hand, we can take the partial derivative of the variable, the function z with respect to y, right? And in this case, we hold x constant, but we differentiate the y, right? So we are going to have a very similar idea here as far as integrating, right? Using partial integration, for example. Let's look at this couple of examples, right? So in this case, we have to integrate the function 9x squared y to the 4th dy. In this case, we are integrating with respect y, right? That means everything that has x's will go outside of the integral, right? So what I'm going to do here, I'm going to rewrite the integral, right? So this is going to be the integral from 1 to x cubed. Okay, this is not easy to read. 1 to x cubed. And oh, wait a minute, no, I was supposed to pull out the other variable, 9x squared, pull it out of the integral, integrate from 1 to x cubed, and y to the 4th dy. And then to integrate the function, so we're going to focus on integrating the function y to the 4 with respect to y, right? To integrate that function, we only require to use the general power rule, right? So this will give us, okay, 9x squared, which is outside of the integral, which is just a multiple constant, right? 9x to the 2nd power times the integral of y to the 4, which is y to the 5th time divided by 5. And evaluated, in this case, be careful. The books would just tell you to evaluate it from 1 to x cubed, right? Which is, there's nothing, no, not x cubed, yes, x cubed, which is nothing wrong with writing it that way, right? That's what most textbooks do, or other references out there, right? However, when I just write it this way, it would be a better idea to be clear which variable we are evaluating, that x cubed and that 1, right? So I'm going to erase this, because in this case we are integrating with respect to y. I'm going to be very specific to say evaluated from y equals 1 to y equals x cubed. That means the following. That means that we only plug in x cubed, the upper limit, right, wherever we see the letter y. And likewise, the lower limit, wherever we see the variable y, right? That's essentially what we do. Okay, so let's apply the fundamental theorem of calculus, right? Let's 9x squared over 5, that's constant. And in this case, I'm going to write quantity to the 5th power minus quantity to the 5th power. All right, so what are we going to plug in there? Okay, upper limit, which is x cubed, minus lower limit, which is just 1. All right, the rest would be just simplifying the powers, right? In this case, we have the power of another power. Okay, let's use a different color to highlight. The power of another power, what do we get? We multiply the power 3 times 5. This is going to be 15. Okay, so we're left with a 9x squared divided by 5 times x to the 15 minus 1. All right, and if you want to distribute this, you could distribute, otherwise you can leave it like this, no big deal. Okay, so that's one example of partial integration. All right, okay, let's do another example. Let's do the following example. In this case, we have the integral of the function for xy with respect to y, right? In this case, we also integrate with respect to y the same way we did it with the other example. And if we evaluate this function from 4 to the square root of y, by the way, as opposed to other integrals that you have learned before, the limits of integration on when it comes to double integrals could be just pure numbers, just constants, or algebraic expressions that depend on y or x, right? We're going to look at different examples later in the lecture. All right, so let's see. In this case, we are integrating with respect to y. Let's write outside of the integral everything related to x, right? In this case, 4x times the integral from 4 to the square root of y dy. Okay, so in this case, all we have to do is integrate the function y, right? Integrate the integral of y, which will be, okay, so 4x y squared divided by 2, right? Evaluated from y equals 4 to y equals square root of y. Again, recall that we are integrating with respect to y, so that's why I'm specifying this, right? I'm specifying these y's, right? And the reason why I'm highlighting this and I stress a lot on this is because there will be a lot of room for silly mistakes and do the evaluation on the other variable as well. But no, in this case, because we evaluate only with respect to y, okay, then we integrate with respect to y, then plug in the upper limit and the lower limit only in the variable y, okay? So 4 divided by 2, that reduces to 2 over 1, which is 2, all right? Giving us 2x y squared evaluated from y equals 4 to y equals the square root of y, right? All right, so let's see. 2x times quantity squared minus quantity squared, right? Which is the integral in this case. Let's evaluate the upper limit here. The upper limit and lower limit. Square root of y and then 4. And let's just simplify this. Okay, notice something. Notice on the first term, the radical sign cancels out the square. And we get 2x. And then we get y minus 4 squared, which is, whoops, something didn't come out very well here. Okay, 2x times y minus 16. All right, and that's final answer. So this is just to give you the idea that when we evaluate double integrals, all we do is do do the integral with respect to one variable first, and then the integral with respect the second variable afterwards. But before moving on to double integrals, let's define what they mean. Let's define what they what do they do when we evaluate. But first of all, we need to define regions, rectangular regions, right, which are the simplest regions, right? The simplest regions that we do. Okay, so let's go back to Math 121, in which you learn the integral, right? F of x is obtained by integrating. Okay. Okay, never mind. Okay, so suppose you have the following. Okay. Okay, suppose you have just a very generic region, right? And this will take us back to the definition of what the integral is, right? So we want to find the area inside, right? Contained from the points A to B, right? So the area, right, the integral will give us the area, which will be the integral from A to B of the function, the given function f of x dx, right? So again, this is f of x, right? And we are looking for the area, right? So we integrate over an interval. Okay, so we order over an interval that goes from A to B, all right, including the endpoints A and B, all right? So that was the simplest form, right? Okay, now let's go back to regions, right? So when it comes to evaluating double integrals, we are going to use them to find volumes, right? And those volumes, so suppose we have a solid in 3D, and then you step on top of the solid with vertex B, right? This is what you will see. You will see the x-axis here, which I'm going to highlight, right? The x-axis, right? And then the y-axis, right? That's what you would see if you saw the region from the top, right? In this case, where instead of integrating over an interval, we, for double integrals, right? Double integrals, we integrate over a region. It's over a region as opposed to a simple integral. The simple integral, right? We integrate over an interval, right? A line, if you will, right? I mean, an interval. In this case, it's over a region R, right? Creating this area, right? Giving us this area. So in this case, there are different ways to denote, okay, notation, all right. Let's look at that. So notice the x-axis, right? The x-axis goes from A to B, right? So the notation is A, the inequality way, right? That you may have seen before. And on the other hand, we have C to D on the y-axis, right? That's one way to denote it. There is another way to denote using like interval notation, A going to B, right? And then multiplication sign, C to D. All right, so that's the other way to denote regions, right? For example, the rectangle that goes from, let's say, okay, this one, well, this looks like a rectangle. This is going to work out. Let's say this one goes from 1 to 4, right? And then let's say this goes from 1 to 6, right? So we would say this region would go from, as far as x goes, from 1 to 4, and as far as the y direction goes, from 1 to 6. All right, using the other notation, it goes from 1 to 4. Whoops, not parentheses, actually brackets here. All right, and as far as the vertical direction, it goes from 1 to 6. Okay, two different ways to denote it depending on how you read it on the textbook. It might use either one, right? All right, now let's look at the geometric aspects of this, right? Okay, so let's go back to the picture I drew before on the side of the other page, right? So what happened when we found areas, right? You might remember the intuitive idea of finding the of evaluating the integral, right? So in this case, it's actually what it means, right? If we divide it by rectangles, right? We divided by rectangles, and then we added the area of those rectangles, right? However, if we subdivide it, or rather if we partition that region into, let's say, 5 rectangles, well, remember there was room for finding inaccurate area, right? Because some of the area was left out, right? So the idea was to increase, right? To increase the number of rectangles. When we increase the number of rectangles, we get a more refined, right? A more refined area, right? And giving us, every time as we get close to many many rectangles, right? So the idea is to sum, right? To sum f of x of I times delta x of I, right? That's the length. Okay, let me denote this. Length and times the width of the rectangle, right? And in this case, well, we consider the idea of starting with the first rectangle and then at n, right? N rectangles. However, if we take the limit and we make n approach to infinity, that was where the integral came from, right? So in a similar way, right, we are going to define what the double integral is, right? So in this case, instead of having a plane region, right, we are going to have a solid region, which is the solid region I'm highlighting here, right? But now, how are we going to do these partitions? Now, look at the second picture. Okay, look at the second picture and notice how the base of the solid, right, is partitioned, right? See the floor, what I'm highlighting in green, right? They are partitioned the plane into smaller rectangles. So in this case, by partitioning into smaller rectangles and then finding the height, we are going to get not the area of a rectangle, but rather the volume, right? The volume of this rectangular solid that I'm highlighting, right? So this is just one element, right? Finding the area of only one, I mean not the area, but the volume of that rectangular solid, right? The thing is, look at the partition on the rest of the region in green. We can do the same, right? We could do the same by creating another solid here, right? See what I'm doing here? I'm creating another solid. It's not perfect, but it's giving us the idea at least, right? And this device is not the best to draw, and then draw the solid, right? So notice this box right here, I'm drawing in blue, right? Or maybe I should use a different color. Okay, let me do it here. Okay, so that's one. That is another one right here, right? I'm looking at the heights of, oops, it's kind of hard to draw this, okay? And we get the volume of this rectangular box that we have here, right? So the idea is just the same way as we added the areas of each rectangle to find the integral, we are going to add the volumes of those rectangular boxes to get the volume of the solid generated by the double integral, right? So in this case, the idea is, okay, volume, how do we find the volume of a solid? Okay, the volume of a solid, well, in general, we're considering a rectangular box with length, width, and height, right? Where are we going to get that length, and where are we going to get that width, and where are we going to get that height? Okay, so notice this delta x, right, which is the increment, right? That's the length of the solid, right? That's the length. I'm going to call that L. And then this delta y that I'm highlighting here, that's going to be our width. Okay, let me set that equal to the width. And this height, right, it's going to be the height of the solid, right, which is going to be no other than z, right, the height zx, delta x, delta y, and the height, which is z, right, which will be, oops, which will be that h, right? So writing this in the following terms, right, we're going to have the following. We're going to have the length, which is delta x, times the width, too low, okay, times the width, which is delta y, times the height, which is z, right? But in this case, z is given by the function. Let me write it in terms of the function, delta x, delta y, and f of x, y. Okay, notice this is what we have over here, right? That's the volume of the rectangular solid, right? Which in this case, they here on the text, on the book where I got these notes from, they wrote the height first, then the length, and then the width. But originally we go with the idea length times width times height. But again, this is multiplication order, doesn't matter. But just for the sake of notation right here, right? So we typically get the volume of the rectangle, okay? The volume of the rectangular solid, right? Which in this case, okay, let me erase this equal sign. This will be f of x, y, delta x, delta y. Now, the same way, if we add all those solids, all those rectangular solids, so if we add the volumes of all, and in parentheses I would say infinitely many rectangular solids, this gives the volume under f of x, y, right? And the formal form right here is given right here, right? So in this case, here is the summation form, right? This is the length. This is the width, and this is f of x of y, y sub j, and this is the height, right? And then we are going to add this, right? However, notice there's two ways to express this, right? So the idea is to make this delta x and delta y to go to 0, right? The smaller those deltas are, the better, right? Because those deltas being the smaller and smaller gives rise to infinitely many, right? So this is the same as saying the following. Okay, let me write it in a different way. So we're gonna have the limit of delta, I'm gonna change delta x for, let's see, I'm gonna change notation here. Okay, let me write the summation of this, right? Oh, come on. Okay, f of x sub y, y sub j, okay, delta x, delta y. So we want to have m and n go to infinity, right? Having I equals m, j going to n, m comma n, having infinitely many a partition of infinitely many rectangular, let's see what's going on here, infinitely many of this, right? So that's what we do. But again, this notation might be a little bit weird to even read, right? So luckily we are not going to evaluate these integrals using the long method, right? The definition method, right? Just the same way there is a limit definition to evaluate the derivative. Remember Math 121, right? Those were a little bit painful, right? And there is also a painful method to evaluate integrals and double and triple integrals using limit definition. It's called by evaluating Riemann sums, but this is not what we're going to do. The Riemann sums, we just mentioned them real quick in terms of, in a nutshell, to partition a region or a solid region, right? A plane region or a solid region, and then just add those areas or those volumes to compute the single integral or the double integral respectively. Okay, so let's look at one example. Okay, so iterated integrals, right? This will give us as well the volume of the solid, right? So, okay, let's evaluate the double integral, right? Denoted double integral with a subscript r. This subscript r, right, will be, okay, the subscript r is the region, the rectangle defined by 1 to 4 and y by 1 to 2, all right? And the function that we integrate will be the function f of x, y equals x plus 2y, okay? Now, let's see. So, let's set up the integral, okay? Let's set up the integral. So we're gonna have, I'm gonna write it down, f of x, y dA, okay? Now, what is dA? This dA will be replaced with dx dy or dy dx, depending on the order, right? So first I'm gonna do, okay, let me write down the function f of x, right? Which in this case is the given function, right? In this case, x plus 2y dx dy, okay? So let me highlight the function, right, that we are working on. All right, here is where we need to pay special attention, right? So notice x, okay, let me actually circle. X goes from 1 to 4. So we are going to evaluate the integrals inside out. What do we mean by inside out? Okay, so we are going to have an innermost integral and an outermost integral. So the innermost integral, right, will have the dx, right? And the outermost, okay, let me call this inner. And the outermost integral will be the one outside of the symbol of the integral going with xy, right? So you write outermost. Okay, so first we are going to evaluate the integral with respect x, and then we are going to evaluate the integral with respect y. Okay, how are we going to do? Okay, look at the limits of integration. So in this case, dx goes first. So look at the limits with respect x. That's going to go from 1 to 4. All right, it goes from 1 to 4. Let me highlight with that color I'm going to use orange here. Highlight the limits, right? And highlight the dx just to denote that this will go with the limits corresponding to the x, right? Now, the outermost integral, which will be integrated with respect to y, has the limits with respect to y, which we have them here. It goes from 1 to 2. Okay, so let me use a different color here to highlight this. I'm going to use, how about yellow? Okay, highlight the limits and highlight the dy just so you can keep track of this. And that's going to be the second integral that we evaluate, okay? So that's how we set up the integral. Notice all this in colors, right? Step by step. Another thing that I'm going to do, okay? After a while, after practice, you don't have to do this, but I like doing this at the beginning just so you can see how are we evaluating this integral. So I will open a big bracket so I can focus on the integral that we are going to evaluate first. Okay, x plus 2y dx, close the bracket, dy. Okay, so we are going to focus on evaluating the integral I'm highlighting in green right here, right? So let's focus on evaluating that integral first, okay? However, I'm going to write a series of additional steps. Notice that we have two terms, right? We have the first term x and we have the second term 2y. That means we are going to write down two individual integrals. Okay, how are we going to do that? Okay, let me go down here. Okay, so this is the same as saying the integral from 1 to 2, right? And I'm going to write this the integral of x dx, right, from 1 to 4, plus the integral of 2y dx. Okay, that goes from 1 to 4 dy. All right, so that's the following step that we do for now. Okay, for now, ignore the dy and ignore the symbol of the integral going from 1 to 2. We're going to leave those two that I've just highlighted. We're going to leave it for the end, okay? So we're going to leave that for the end. And then, okay, I think I'm running out of battery. Give me a second. All right. Okay, got it. So we're going to evaluate now the integrals that I'm highlighting in purple individually, right? And notice that the first integral, right, the one I'm calling number 1, has an x on the integrand, and we are integrating with respect to x. The second integral has y's inside, but we're integrating with respect to x. So those two y's, I'm going to take it outside of the integrals just the same way we did it earlier, right? By when it came to do the partial integration. So let me go ahead and do that. Okay, so that's going to be equal to 1 to 2, integral from 1 to 2 of the function. Okay, I'm not going to integrate this one even though this is ready, right? X dx plus 2y, right? That goes outside of the second integral sign, right? Because the integral only depends on x, right? So then the y. Okay, so now we're ready to evaluate these integrals. Okay, so the integral from 1 to 2, right, times, okay, so this will be the integral of x with respect to x. We can just use the general power rule. That's going to be x squared divided by 2. Okay, that's the integral. And then plus 2y times the integral, right, the integral of dx, right, the integral of dx. Well, in this case, the integral of dx is just going to be x, right? But in this case, we are not going to write plus c. We are going to evaluate this from 1 to 4. But again, keep in mind what I mentioned earlier when we were looking at the partial integration. If I just write the limits going from 1 to 4, it is not clear, right? It is very easy to go from here, from this step right here to that step without keeping in mind that we are integrating only with respect to x. So that's why I'm going to change this to x equals 1 to x equals 4. That way is more explicit about which variable we're integrating to, right? Now, let's do the evaluation. Okay, so this will be the integral, right, from 1 to 2. All right, it's going to be the integral from 1 to 2. and this is going to be quantity squared over 2 plus 2 times y times quantity, and then minus quantity squared divided by 2 plus 2 times y, 2y times quantity. What is that quantity? Okay, then the y. Okay, that quantity will be for the upper limit. Okay, this will be the upper limit going from 4. Okay, let me use a different color here. That's for the upper limit. And then for the lower limit, which is 1. All right. What are we going to get here? When simplifying this, I get the following. I get, okay, so in this case, I'm going to simplify the quantity that I'm highlighting right now. 4 squared divided by 2. So 4 squared is equal to 16. 16 divided by 2. That's going to give us 8. So the integral from 1 to 2, and then 8 plus, in this case, 2y times 4, that's going to give us 8y. Okay, plus 8y. And then, okay, looks like, never mind. And then what are we going to get here? Okay, for this quantity right here, 1 squared divided by 2, that's just going to be minus 1/2. And then 2y times 1, that's going to be minus 2y. All right, so from here, let's simplify, let's combine like terms. In this case, I'm going to combine the y's with the y's, and I'm going to combine the constant terms with the constant terms, right? So let me do the y's first. 8y minus 2y. All right, so this will give us the following, right? This will give us the integral from 1 to 2 of the quantity 6y plus 15 halves, right? It's going to be a fraction, right? It's going to be a fun to evaluate later on, and this with respect y. So let's split this into 2 separate integrals, or maybe not. Okay, how about the integral of 6y? The integral of 6y, all we do is add 1 to the exponent, the invisible one that we have there. That is going to be 6y squared divided by 2 plus 15 halves of y. And this evaluated again from y equals 1 to y equals 2. Again, keep in mind what I mentioned earlier, right? In this case, now we're integrating with respect to y, right? We plug in the limits, whatever y corresponds, right? So let's simplify things a little bit here. Okay, 6 divided by 2, that's 3 over 1. Okay, so this will be 3y squared. Okay, 3y squared minus 15 halves of y, evaluated from y equals 1 to y equals 2. Okay, let's apply the fundamental theorem of calculus here. Okay, so 3 times quantity squared minus 15 over 2 times quantity minus 3 times quantity squared minus 15 over 2 times quantity. What are going to be those quantities? Okay, so first we are going to have 2 and then 1. Okay, let's go ahead and simplify this. Okay, so here we're going to have 2 squared, which is 4 times 3. That's going to give us 12, right? Minus, notice what we get here, right? Notice what we're going to get here. Okay, by the way, it's not going to be minus. I was making a little mistake here. This is supposed to be a plus. All right. This is supposed to be a plus plus. Okay, let's divide out these twos, right, to get a 15. And then minus the quantity 1 squared, which is 1 times 3. That's going to give us a 3, right? Plus the quantity 1 times 15 over 2. That's simply 15 over 2, okay? And let's simplify this. So 12 plus 15, that's going to give us 27, right? Minus 3 minus 15 halves. And if you use your calculator to simplify this quantity, you should get the quantity 33 halves. So that's our final answer. Notice we're getting a positive value, right? Because we're finding volume, right? The double integral represents a volume, so no wonder we get a positive number, right? Now, one of the most important things that we need to cover here is reversing the order of integration, right? Notice what happens here. Okay, let me highlight the important things about these integrals, right? We have a function, so the integral from c to d, the double integral a to b, c to d of the function f of x, y. So notice first we evaluate the integral with respect to x, right? And when we do that, we apply the fundamental theorem of calculus, that is f of b minus f of a, but we only plug in the x values, right? So notice I'm highlighting with the corresponding color. Once we're done with that, right, let's see. dy, we do the second integral, but now we use the same, the other limits of integration. So now this is the same as doing the following. Notice we can reverse the order of the integration. I'm going to keep green. Notice we're now going to integrate with respect y. So we reverse the limits, right? We reverse the order of the limit. Notice we are reversing the order of the integral signs, right? So on the other hand, when we do the second integration, the second iteration of the double integral, in this case, this is going to be from a to b, right? So in other words, this is what happens. The limits change and the order of the integration also gets reversed. Okay, to verify this theorem, we are going to evaluate the same integral we just evaluated on the example above, right? That is, evaluate the double integral in example 2 by reversing the order of integration. All right, so in this case, we are going to evaluate exactly the same function, right? Exactly the same function. Let's see. We're going to evaluate double, okay, double, and that's the function x plus 2y. But instead of evaluating with respect x first and then with respect y, we're going to do with respect y and then with respect x, okay? In this case, the limits with respect y go from 1 to 2, and the limits with respect x go from 1 to 4. Notice how everything is reversed. Let me scroll up a little bit again so you can compare with that. Okay, so notice we have from 1 to, okay, let me use a different color here, something to highlight, from 1 to 4, and then from 1 to 2, all right? And then the x first and then the y afterwards. Notice now, go to the second example, which is the same integral, but everything is reversed. Okay, so I'm going to do the same as I did before. I'm going to integral from 1 to 4. And I'm going to evaluate the integral, the innermost integral from 1 to 2 of the function x plus 2y, okay, with respect to y. And I'm going to save the dx for the very end of the problem. So now I'm going to split this into two separate integrals, right? Again, you don't have to do all this. You might want to just integrate these two because this is easy to integrate. However, I'm going to do all the steps. Maybe it will be, because I think it will be useful for you to see what's going on. So we're going to have the integral from 1 to 2 of the function x dx plus the integral of the function to y with respect x. Oh, wait a minute. This is not with respect x anymore. We do respect y first and then respect y, then respect x rather, okay? All right, let's analyze the first integral. The first integral, notice we have an x in the integral. However, we are integrating with respect to y, right? So I'm going to pull that x outside of the integral. Okay, let me go to the following line, okay, from 1 to 4, right? So this will be x times the integral from 1 to 2 dy plus the integral of 2y dy. Well, in this case, the y is with respect to y. However, all I'm going to do here is pull out the constant term, this constant factor rather, which is the number 2. And then I'm going to integrate these two babies right here with respect to y. All right. Okay, so the integral of dy will be, okay, integral from 1 to 4, the outermost integral. This is going to be xy, right, plus 2y squared divided by 2. All that evaluated, again, be careful here. Notice we are evaluating from y equals 1 to y equals 2. It might be a good idea to divide out common factors, divide out those 2's, right? That way we get a simpler version of the integration of the integral, right? So we are going to end up with, oh, we're missing the dx here. So I'm going to have the integral from 1 to 4 of xy minus, oh no, not minus, plus y squared evaluated from y equals 1 to y equals 2. Okay, so let's use the fundamental theorem of calculus for the inner part of the integral, right? That will be x times quantity plus quantity squared, right? Minus x times quantity plus quantity squared. That times dx. All right. Okay, so we're going to plug in the upper limit first, which is 2, and 1, which is the lower limit. All right, and let's simplify this. Okay, this, I guess, simplifies really easily, right? So we are going to have the following. We are going to have 2x, integral from 1 to 4 of 2x plus 4 minus x minus 1. Notice this, these negatives right here, the ones I'm circling, right, come from distributing this negative sign over these two terms. X times 1 is this x right here, and 1 squared equals to 1, right? Okay, let me get rid of those arrows right here. And let's close parentheses here. So we're gonna have times dx. Notice now this reduces to an integral that depends only on one variable, and we integrate with respect to one variable, right? So x's with x's, constant terms with constant terms, all right? Okay, let's simplify this. So 2x minus x, that's going to be the integral from 1 to 4, and that's going to be x minus 3. All right, x minus 3, not minus 3, plus 3, x plus 3 dx. Okay, so we can integrate this easily. That's going to be x squared divided by 2 plus 3x. We're using the general power rule, right, from here to this step. And we evaluate, in this case, from x equals 1 to x equals 4. Okay, so let's see. Quantity squared divided by 2 plus 3 times quantity squared minus quantity squared divided by 2 plus 3 times quantity. And the quantities are for the upper limit, again, 4 and 1 for the lower limit. Okay, let's simplify this. Okay, 4 squared, which is 8, right? 4 squared, which is 16, divided by 2. The first quantity I'm highlighting here with purple, that's going to give us an 8. Okay. Plus 3 times 4, which is 12. And then minus 1 squared right here. 1 squared divided by 2, that's going to give me 1/2. Plus 3 times 1, which is 3. Okay, so 8 plus 12, that's going to give us a total of 20. Minus 1/2 plus 3, which is going to be, minus 3 rather, not plus 3. And that's going to give us 17 minus 1/2, which is the same as 33 divided by 2, which is the same quantity we obtained when evaluating this integral within the other order. Okay, so that's one example of a double integral doing with respect x first and then xy, and then in this example, this second example, exactly the same function using the same limit but taking a different order. And not surprisingly, well, we get the same. Okay, now let's look at another example. Okay, so we are going to have the integral of the function y squared times e to the negative x, where r is going to be x going from 0 to 1 and y going from -1 to 1. And yes, this integral we're going to evaluate it to using the two orders of integration with respect x first and then respect y, and then the other way around. All right, so let's set up the integral. Let's begin with that. Okay, so double y squared e to the negative x dx dy. Okay, dx dy. So with respect x, this goes from 0 to 1, and with respect y, it goes from -1 to +1. Okay, so no big deal, hopefully. Okay, let's integrate the innermost first, and to do that, I'm going to write the outermost brackets, the innermost. Now notice something here. So in this case, we are evaluating the integral with respect x, right? We're evaluating integrating this function with respect x. So all factors that do not have x, in this case, the y squared, I'm going to write it outside of the integral, right? So I'm going to write this as the integral from -1 to 1 times y squared times e to the negative x dx evaluated from 0 to 1. Okay, that differential of y. Okay. Okay, so now let's integrate the function e to the negative x. The integral of e to the negative x, let's recall the formula, right? So the formula to integrate e to the ax. Okay, let me write it down here. Integral of e to the ax dx equals to e to the ax itself times 1 over a, right, plus c. Or if it's like in this case, it is a definite integral, well, we don't use the c. However, what I want you to see is that we are going to divide by the quantity that multiplies the x. In this case, for the integral, okay, let me do it on the side, the integral of e to the negative x dx equals 1 over negative 1 e to the negative x, right, plus c. But what is that 1 over negative 1? Isn't that the same as saying negative e to the negative x? All right, so this is what we're going to have for that integral, right? That's what we get. Okay, so let's go ahead and go back to the example right here. Okay, so we are going to write integral from negative 1 to 1 y squared times negative e to the negative x, right? Evaluated again. Notice, keep in mind that we are integrating with respect x. X goes from 0 to 1. All right, and then dy. All right, let's get rid of all these parentheses right here and fix all these negative signs, right? Okay, let me clean this up because it looks a little bit messy. Again, I'm doing every single step. That's why we're getting those parentheses and those negative signs, right? So let's see. Okay, so we're going to get the following. We get, oh, hold on a second. Something weird's going on here. All right, got it. All right, so we're going to get the integral from negative 1 to 1 of negative y squared e to the negative x. That evaluated from x equals 0 to x equals 1. And then times dy. So now let's apply the fundamental theorem of calculus on this one. Okay, so this will be equal to the integral from negative 1 to 1. And this is going to be negative y squared times e to the negative quantity minus e to the negative quantity. What is that negative quantity? E to the negative 1 minus e to the negative 0. But well, what do we know about e to the 0 power? That goes always to 1, right? Any quantity to the 0 power is always 1, right? So we get the following. We are going to get, we're going to get the integral from negative 1 to 1 of negative y squared times e to the negative 1 minus 1. All right. Now, there's a few things bothering me here. So the couple things bothering me here is, number one, this negative sign, right? And at the same time, too many parentheses, right? That's a little bit confusing. Parentheses here, parentheses everywhere. So this is what I'm going to do. I'm going to use the distributive property, right? To distribute the negative sign over these two terms right here. So what are we going to get? Okay, we get the integral from negative 1 to 1 of the function y squared times, okay, keep in mind that every time you distribute a negative sign over a sum of terms, well, that changes the sign of everything inside of the parentheses. Or if you have a positive term and then a negative term, you can just reverse the order of the terms, right? So times 1 minus e to the negative 1 dy. All right. So that's the integral we end up with so far. Okay, what's next? Notice something. This 1 minus e to the negative 1, this is just a numerical constant, right? This whole thing, put it outside of the integral. That's just a silly number. It doesn't have any y's, it doesn't have any x's, no variables. It's just a number. Yeah, it's kind of funky looking one if you ask me. I agree, but it's ultimately a number. So 1 minus e to the negative 1 times the integral from negative 1 to 1 of y squared dy. And everything reduces to integrating y squared to the second y to the second power to obtain the following. 1 minus e to the negative 1 times y cubed over 3. Okay, so this is what am I going to do? Oh, by the way, this has limits going from y equals negative 1 to y equals to positive 1. So 1 minus e to the negative 1 that divided by 3 that multiplies quantity cubed minus quantity cubed. All right. So we're going to get 1 for the upper limit and negative 1 for the lower limit. Now be very, very careful. This 1 to the third power is going to give us a 1 here, and this negative 1 to the third power is going to give us a negative 1. Negative times a negative 1 is going to turn into a positive 1, right? So this will be 1 minus e to the negative 1 times 2, which is the one that comes from here, divided by 3. If you want to write this in a nicer way, this is 2 times 1 minus e to the negative 1 divided by 3. And you don't need to compute this using the graphing calculator. I'm on the exam, right? I'm going to ask you to leave it like this, okay? So that's another example of a double integral, right? And of course, we are going to evaluate this integral, this very same integral, but reversing the order of the integration, okay? Let's write it down again. So this is what we have, right? So we're going to have the double integral, double y squared e to the negative x, but in this case, we are going to integrate with respect y, then with respect x. So the limits would go from negative 1 to 1 first with respect y, and then they will go from 0 to 1 with respect x. Okay? All right, so let's write down the integral again, 0 to 1, big bracket, just to focus on the innermost integral. Negative 1 to 1, y squared e to the negative x. All right? First with respect y. And then we are going to leave the dx for the very end. Again, let's look at the integrand, right? Y squared times negative x. Notice we're integrating this time with respect to y first, so everything that doesn't have a y, write it outside of the integral, right, as a multiple constant, right? So this will be the same as saying the integral from 0 to 1, all right? And that's going to be, I'm going to write down the e to the negative x outside of the integral sign, go from negative 1 to 1 and integrate y squared dy. That with respect x. All right. Let's see. Then we're going to integrate the function y squared, which will be will be 0 to 1 e to the negative x. The integral of y squared will be y cubed divided by 3. That evaluated again, be careful with this, from y equals negative 1 to y equals to 1. That times dx. Okay, so the integral with respect integral from 0 to 1 of e to the negative x over 3 times quantity cubed minus quantity cubed, right? The multiple constants, I'm leaving them outside of the integral, right? And then the x. So the upper limit here will be 1, the lower limit will be -1, and this is very similar to what we obtained earlier on the other way to integrate the integral. This is 1 minus -1, right? So this is really 1 plus 1, which will give us a 2, right? The integral from 0 to 1, okay? This will be from 0 to 1 of basically 2/3 e to the negative x. Where is this 2/3 coming from? Okay, this adds up to 2. But this is multiplying, this gets multiplying with e to the x here, right? And this 3 in the denominator is the denominator of the 2/3 here, right? I'm going to write down the 2/3 outside of the integral, 0 to 1, e to the negative x dx. Okay, so I'm going to integrate e to the negative x again. So this will be 2 to the 2/3 times negative e to the negative x, right? Evaluated from x equals 0 to x equals to 1. Okay, let me clean up this negative and these parentheses right here. Okay, so this will be the negative 2/3 e to the negative x evaluated from, okay, from x equals 0 to x equals to 1. All right, so negative 2/3, this is e to the negative 1. Well, that means e to the negative quantity minus e to the negative quantity. So e to the negative 1, e to the negative 0, and just the same way we did it earlier. All right, this is going to go to 1, and this is simply e to the negative 1. Okay, so we get the following. Negative 2/3 times e to the negative 1 minus 1. Or if you want to, again, if that negative sign bothers you, all right, distribute it, and this is 2/3 times 1 minus e to the negative 1. And not surprisingly, we get the exact same result as what we did earlier. Let me scroll up a little bit, right? 2/3, right? 2 over 3, or 2/3, it's the same way. I'm just writing it in a different way, right? Notice the order 1 minus e to the negative 1, 1 minus e to the negative 1. Same thing, right? So regardless of the order of integration, again, you should get the same answer, okay? Okay, let's move on to a different topic. Now, what about for this integral, for the integrals that we did earlier, right? We were integrating over rectangular regions. So what if we integrated over plane regions, right? So in this case, we're not talking about rectangular regions, right? Let me write down the picture we looked at before, right? Ranging from A to B and from C to D, right? So in this case, we may have different functions forming a funky looking region to integrate over, right? Okay, so in this case, let's just do an example to show you how this works. Okay, so suppose we want to integrate the function f of x given by f of xy, not f of x, f of xy equals x squared plus y squared. And in this case, R is the region bounded by g of x, by g sub 1, x equals x. Okay, so that's the first region, and this is the second region. All right. Okay, let's see. Let me try a utility here so I can write a grid maybe. No, not a grid. Okay, I'm gonna try this. Okay, maybe. Okay, because if I do this, I'm gonna get that line. All right, that's what I want to do. Okay, so however, how can I rotate the angle for this ruler? I know there's a way to do it. Let's see. Remember, there was a way to do it. No, not share. No notifications. Not really. This is the right equations. Okay, shapes. I guess I'm going to use shapes right here. Hopefully that works. However, this is not what I want. I want the shape right here. Okay. Okay, I think I got it. Okay. Yes. Okay, so this is what it's going to work as our grid, and I'm going to roughly divide this into 1, 2, 3, 1, 2, 3. All right. 4. Oh, I think I remember how to do this. Okay, I think it has to be with the fingers. Oh, I see. Okay. So I'm going to plot the points for g of x1, which is y equals x, right? That's 1, 1, 2, 2, 3, 3, right? Okay, let me connect the dots. I'm going to use a different color for that line, okay? And let me draw this. This is really nice. Okay. And then we are going to have y. I'm going to use orange for y equals to x. In this case, if I plot 2x, this is going to be, if I plug in 1, I get 2. If I plug in 2, I get 4. Right? I get 4. Okay, so I'm going to use the ruler again, and I'm going to twist this. And this is what I'll get. I'm going to get the following. All right. So that's the region over which we will integrate. Okay. Now, what about this third condition right here? X goes from 0 to 2. So x goes from 0, 1, 2. So we are going to integrate over this region right here. All right. Okay, so let's set up the integral to evaluate this integral, right? Let's set it up. So double x squared plus y squared. In this case, so I'm not going to do both orders of integration. In this case, I'm going to do only one order because otherwise it is going to take forever. All right, so let's see. I'm going to do only one order. In this case, I'm going to do dy first. and then the x. Okay, how do we do the y first and then x? Okay, so the limits, the first limits, right, the ones in which I'm going to highlight where I have empty spaces, right? Here I'm going to go the vertical direction. In other words, I'm going to consider the following. This is the lower function and or the lower graph. This is the yellow one, the upper, right? So we are going to integrate from lower to upper. In this case, the lower, which is y equals to x, and the upper, which is y equals to 2x. So the limits of integration here for the integral, the innermost limits are going to be from x to 2x. Notice we're not going to go from 0 to 1, from 1 to 4 like the other integrals. So now we're going to have actual functions bounding that region. And for x, right, so that's for y. It would be worth to highlight this, right? All right. Now for x, okay, let's highlight the x's. I'm going to write empty spaces here, right? X is explicitly telling us that goes from, okay, in this case, that goes from 0 to 2. It goes from 0 to 2, all right? So let's start working on this integral, okay? Now, first of all, as usual, I'm going to write this 0 to 2. I'm going to do an innermost integral first. That is the integral from x to 2x of the integrand x squared plus y squared. All right. First, we're going to integrate with respect y. And then we are going to integrate with respect x. Okay. So that's what we do. That's how we do this. All right. Okay, I'm going to split this into two integrals as usual. That's the integral from 0 to 2 times, okay. I'm going to write this, the integral from x to 2x of x dy. I mean x squared d, oops. Okay, I'm going to need more space here. To x, x squared dy plus the integral from x to 2x of y squared dy, all right, dx. Okay, let's look at each integral. Okay, so notice we are integrating with respect to y, but we have x squared there, right? I'm gonna write that x squared outside of the integral, all right? Okay, let me use a new, okay, maybe the same line. Okay, so we're going to have the integral from 0 to 2 of x squared, and that goes from x to 2x, all right, dy, plus the integral from x to 2x. In this case, let's look at the second integral. Notice y squared depends on y, so that remains inside of the integral, okay. Y squared dy, and I'm missing an x here. It goes from x to 2x. Okay, let's evaluate each of the integrals now. So this is the integral from 0 to 2, right? And that one, x squared, the integral of dy is y, plus the integral of y squared, it's going to be y cubed over 3. And that whole thing, again, be careful when setting the limit, goes from y equals x to y equals 2x, right? Again, it's always a great idea to set this y equals, right? To write this y equal and or the x equal depending on the order. And that to avoid confusions about what we're supposed to integrate and which variable are we doing the integration, right? So let's see. I'm going to integrate, I'm going to write the integral from 0 to 2. That's going to be, okay, x squared times quantity plus y, oh no, not y anymore, quantity cubed divided by 3 minus, okay, let me scroll a little bit here. I need more space. Minus x squared quantity plus quantity cubed divided by 3. That whole thing times dy. Or rather dx. And here I forgot a dx also. Okay, so let's plug in the upper limit. The upper limit, which is 2x, all right, 2x. And the lower limit, which is x. All right, so this will take a while to simplify, so let's see. When we simplify this, x squared times 2x, that's going to give us next a 2x cubed. Okay, let me go all the way here. The integral from 0 to 2, right, of 2x cubed plus, okay, in this case, the quantity I'm highlighting with blue. Okay, we're going to get 2x, the quantity cube. Be careful when cubing the 2x. That's going to give us 8x cubed divided by 3. And then minus, okay, be careful with this minus, okay. Well, I'm not going to write parentheses. Minus, let me go over here. When we multiply x squared times x, that's going to give us x cubed. And likewise, when we cube the quantity x, we just get x cubed, right? So notice everything is going to be ending up in terms of x cubed, right? So this will be x cubed plus x cubed divided by 3, all right? And that times dx. Okay, let's see, let's simplify this. Okay, I'm going to distribute the negative sign. I'm going to distribute the negative sign here. All right, and this will be the following. This will be the integral from 0 to 2 to x cubed plus 8/3 of x cubed minus x cubed minus x cubed over 3. Okay, notice we have a combination of integers and fractions. Okay, let me combine the integers with integers and fractions with fractions. Notice the good news about the fraction terms is that we have all of them in terms of thirds, right? We have a common denominator, in other words. That's what I wanted to say here. Okay, so no need to find an LCD and finding missing factors. You know the drill for those problems, right? So the integral from 0 to 2, so 2x minus x, 2x cubed minus x cubed, this will be only 1x cubed. And 8/3 minus 1/3, this will be 7/3, right? Nevertheless, we are going to be in the need of writing and a missing factor right here. This x cubed is the same as saying, we have the solution to this one here. What did I get? This is going to be 3/3 plus 7/3. This is going to give us, oh, I forgot the x cubed. This will be the integral from 0 to 2, right? From 0 to 2 of 10/3 of x cubed. dx. Okay, we're almost there. We're almost done with this one. I'm going to write the constant factor outside of the integral so it doesn't bother us, right? Integral from 0 to 2 of x cubed dx. Now let's integrate this integral, right? The integral of x cubed will be x to the 4th power divided by 4. And if we simplify this, okay, 10 goes with 4 twice, right? We can, in this case, we get a 5 and then we get a 2. And then 3 times 2, that's going to give us a 6, right? However, let's write down the limits of integration. In this case, x goes from 0 to 2. All right. Now, we're going to have 5 over 6 x to the 4th evaluated from x equals 0 to x equals 2. Now let's apply the fundamental theorem of calculus as usual, right? So 5/6 quantity to the 4th minus quantity to the 4th. So this will be 2 for the upper limit and 1 for the lower limit. Okay, so 2 to the 4th power, that's going to give us 16 minus 1, which is 5 over 6 times 15, right? Which in this case reduces to 40 divided by 3. So that's the final answer, okay? Again, what does that double integral represent? If we could graph this solid in 3D and then bounded by these two lines, right? Basically two planes in 3D, and we would get that little, like a piece of cake, right? And this is what we get, 40/3, okay? Let's do another example. Okay, let's do another example, and let's see. So now we are asked to evaluate this double integral that will represent the volume under the surface f of x equals x e to the y, right? In which R is the plane region bounded by y equals x squared and y equals x. That's all the information they're giving us, right? That's a very typical problem. In this case, they're not giving us a limit from 0 to 5 or 1 to 2, whatever. In this case, it will be our job to find the intersection points. You'll see. Okay, first of all, let's plot this. Okay, let me plot this same way I did. Oops. I'm gonna use shape. All right, and again, I'm going to chop this into 1, 2, 3, 4, 5. 1, 2, 3. No, this is not going to be useful. I need this bigger. 1, 2, 3. 1, 2, 3. That's going to be good. Okay, let's graph y equals x using green. Okay, let me change this to green. Okay, so 1, 1, 2, 2, and 3, 3, right? So let me use a ruler here. Okay, so let me roughly draw this graph. Okay, don't move. Okay. Okay, let's see. Something's going on here. Okay, let's see if, oh yeah, I got it. All right. Okay, so let's draw this graph right here. It's not going to be perfect, of course. All right, but at least it's going to give us an idea of what this is, right? And in the other case, oh, what happened here? Okay, I don't want the same color for the Cartesian plane. I just want this, okay. And let's graph, okay? Now I'm going to use orange to plot. Okay, let me see if there's a better orange color. Okay, it's right here. Okay, so when 0, 0, this is a parabola, right? 0, 0, 1, 1, and then 2, 4, right? So this is going to go like this. Okay, it's not easy to draw a parabola, right? Okay, I don't know what happened here. Let's just keep it like this. All right. So what is this, the region that we're integrating? We're integrating this tiny region, right? Okay, visually x and y go from 0 to 1, right? 0 to 1. So we can just integrate from 0 to 1, right? However, let's show how we get those limits of integration, right? So number 1, okay, number 1, need to find the intersection points first, right? So we do that first, right? How do we do that? By setting set y1, right, equals to y2. In this case, what is y1? It doesn't matter, right? But let's say y1 is y equals x squared and y2 is y equals x. So what are we going to do here? Okay, this is what we do. That's the key. Set y equals, oh, okay, not into shape. Nope, that's what I was doing. I see. So in this case, in other words, what will we do? Okay, let's set x squared equals to x. This will give rise to the following: x squared minus x. Move all the terms to the left-hand side, because in this case we have a second degree equation, right? A quadratic equation. And in this case, we don't need to go with the quadratic formula. It's enough to just factor out x, solve this equation by factoring, right? So, and this is how we get that x equals 0 and x equals to 1, right? And clearly we can see that in the picture, right? In some cases, the reason why I'm showing you how to find the intersection points first is because you may get other more complicated regions to integrate over, right? And in this case, in those cases, it won't be very easy to see, oh, x goes from 0 to 1, oh, x goes from 1 to 3. No, it may not be that easy. So that's why I show you how to do that. Now let's set up the integral that solves this problem. Okay, let's write down the double integral. In this case, double. All right, and x e to the y. In this case, I'm going to go again with dy first and then dx. Okay, now what are going to be the limits? Okay, let's go back to, in this case, let's go back to both functions. Notice the one in orange is the upper, Okay, upper y equals x squared. And the I meant to say lower, not upper. Okay, my bad. This is the lower. It's the lower function, and the straight line, which is the upper, that is y equals x. Okay, so the limits are going to go from, and I'm going to keep the same color just so you can see where it is coming from. Go from x squared to x, right? So that's in the y direction, right? Because that's upper minus lower, right? Now in the x direction, this is going to go from 0 to 1. And we are ready. We have all the elements now to compute this double integral, okay? Let's see. So again, the integral from 0 to 1, big bracket. The integral from x squared to x e to the y, dy. Close the bracket times dx. All right. Now, notice this integral right here, and I mean the integrand, and notice that this integral is being evaluated with respect to y, all right? So let's see, what are we going to do here? I'm going to write outside of the integral all the factors that do not have a y, in this case just the x. Okay, so the integral from 0 to 1, x e to the y, right? No, not x e to the y, rather x times the integral from x squared to x of e to the y dy. All right, so that's what we do. Okay, we're going to integrate e to the y, which is the quantity I'm highlighting here. And the integral, but the integral of e to the y again is itself e to the y. No need for negative signs or constants, right, to compensate the integrand, right? So this is going to be x e to the y. Evaluated again, keep in mind that we are evaluating a y. We're integrating with respect to y, so the limits are going to be y equals x squared minus and to y equals x. All right. So we're going to get that the x, so this will be the integral from 0 to 1, right? The integral from 0 to 1 of x e to the quantity minus e to the quantity, okay? So the first quantity will be x, and the second quantity, the upper limit, and then the lower limit will be x squared. All right. Dx. And this is where the fun begins here. Notice what's going to happen here. So when we rewrite this integral, we're going to have the integral from 0 to 1 of x e to the x minus x e to the x squared dx, right? So that's what we are going to get here. All right. Now, when we split this into two integrals, this is what we get. Number one, the integral from 0 to 1 of x e to the x minus, dx, minus the integral from 0 to 1 of x e to the x squared dx. So we're going to evaluate those two integrals using different methods, all right? So let's see what's going to happen here. Let me show you something. We are going to evaluate the first integral, right? Number one, by parts. And the second integral, we evaluate it by substitution. okay, using u substitution. All right, so this is what we're going to do here. Instead of writing the whole thing using an integration by parts for one term and then substitution for the other term, I'm going to use the space below, right? I'm going to use the space below to evaluate this integral. So I'm going to do the first one, which is by parts. Okay, so the number one, the first integral right here, number one, by parts. Okay, so I'm going to write the integral from 0 to 1 of x e to the x, all right, dx. So remember from back in, what was that, chapter, I believe chapter 7, when we looked at integration by parts, u equals x and dv equals e to the x dx, all right? So differentiate u, that is du equals dx. And on the other hand, integrate v, integrate dv to get v, which is e to the x, because the integral of e to the x is itself e to the x. Then we are going to use the formula for integration by parts, right? Recall the formula is u times v minus the integral of v du. That's the formula we're going to use to simplify that integral right there, right? Okay, so let's go ahead and do that. So u times v, which is x e to the x, because this quantity has already been simplified. Well, I'm not going to write x here. I'm just going to go and write from 0 to 1, then minus the integral of v du, right? Which in this case is e to the x dx. Go from 0 to 1. All right. This is going to be x e to the x minus the integral of e to the x, which is just e to the x, right? The whole thing evaluated from 0 to 1. All right, now to make things easier, you might want to factor the e to the x. I'll show you. Okay, and then evaluate that from 0 to 1. Now from here, let's do upper limit e to the upper limit, which in this case is 1, e to the first times 1 minus 1, and then minus e to the quantity minus 1. Okay, and in this case, the lower limit, which will be 0. E to the 0, 0 minus 1. Notice something interesting here. When you subtract 1 minus 1, this whole term is going to go to 0, because 1 minus 1 is 0. 0 times any quantity is going to give us what? 0. But we're going to be left with this negative e to the 0 times 0 minus 1, which is negative 1. But again, what is e to the 0? E to the 0 is 1, negative 1 times negative 1, which will give us a positive 1. Okay, so we may go back to the first integral that we did by parts and add a 1, right? Okay, 1 minus, now I'm going to write the result of evaluating the other integral using u substitution, right? I'm going to denote this with green just to agree with what we have here. Number 2 by u sub. Whoops. All right, u substitution, that is. Okay, let's see. The integral from 0 to 1 of x e to the x squared. Notice the space I'm leaving here, because in this case, when we do the substitution, u, right, equals x squared, which is the quantity that is on the exponent of the exponential function. Then I'm going to do the u, which will be 2x dx, right? Notice I'm missing the dx here. So we have the x dx, right? The x dx. However, we're missing a 2. We can add the 2 right here, provided to divide 1 out. Now, on the other hand, there is something you might want to do here. You might want to do the following. So you don't do substitution and then back substitution, right? Do u evaluated at 0 and u evaluated at 1. And that to avoid a lot of substitutions, right? So 0 squared, rather to avoid the back substitution, and then 1 squared. Actually, the new limits in the world of u are going to be the same. So this is what we're doing. So we are given an integral in the world of x. We're doing a u substitution to take this integral to the world of u, which will be a world in which the integral can be evaluated more easily. The thing is, if we rewrite the integrand in terms of the world of u, then we have to rewrite the limits, their corresponding transformation in the world of u as well. All right, so let's see. So this will be 1/2 times the integral from 0 to 1 of e to the u du. But again, the integral of e to the u is simply e to the u evaluated from 0 to 1. And in this case, all we have to do is 1/2 times e to the first minus e to the 0, upper limit minus lower limit. But again, what is e to the 0? E to the 0 is 1, right? And that's the answer to the second integral. Now let's go back here to 1 minus 1/2 e minus 1. All right. And what am I going to do here? I'm going to distribute the negative 1/2 over the two terms to get the following: 1 minus 1/2 of v plus 1/2. What are we going to get here? This is what we get. 1 plus 1/2, that's going to give us 3/2, and then minus 1/2 of e. And you might want to factor out the 1/2. Factoring out the 1/2 would give us with a 3 minus e inside of the parentheses, and this is the grand final answer to this integral. Okay. Yeah, so this one was kind of a big problem, long problem, right? Let me recap. Okay, let's recap. So in this case, they're not giving us any information about the intersection points or the limits of integration, so we find them ourselves, right? Over here, setting the two functions equal to each other and solving the polynomial equation, right? Then we set up the integral, right? We split it into the inner integral and then the outermost integral. Now, in this case, when evaluating the innermost integral to evaluate then the outermost integral, we were in the need of evaluating two integrals, one by parts, the other one by u substitution. So that's why I use all the spaces below here and then put everything together into here to come up with the final answer, right? Which is what I'm highlighting here as well. All right, let's do one more example. The last of them, by the way, right? So let's see. Let's look at this one. All right, so let's see. So we want to evaluate the function. Oh, by the way, I don't think I gave you the function right here. So I'm going to give you, okay, let me write it down here. So f of x, y equals the function, what was that? X, another exponential e to the y squared. All right. This one is going to take another while, another good minute as well. All right, let's see. In this case, let's plot the region of integration, right? Let's plot the region of integration. We'll write with blue. All right, and then, okay, they're telling us that the plane region is bounded by the y-axis or x equals 0. So the y-axis itself, I'm going to highlight this, right? It's worth to mention that these two sentences mean the same. Right? X equals 0 is right, the y-axis, right? And then the horizontal line, y equals to the 4. Okay, let's first of all divide this Cartesian plane into 1, 2, 3, 4, 5. That's enough. 1, 2, 3, 4. All right. So the horizontal line that I'm going to highlight in green, right? And I will also use green to draw that horizontal line, all right, at y equals to 4. Okay, let me put the ruler correctly, and I'm going to use green, all right. Well, actually, well, never mind, that's okay. Green. Okay, and let me get rid of the ruler. All right, that's the horizontal line, and the graph of y equals x squared. All right, now let's see. Y equals x squared, which again is a parabola. If x equals 0, 0 squared will be 0, right? 0, 0. 1 squared is 1, and then 2 squared is 4. Okay? In this case, we will... Oh, this didn't come up nicely. Let me see if I can do it nicely. Oops. It's not really easy to... Okay, that's my best as far as drawing the parabola right here. And here I'm going to give this away. So on the previous example, I asked you to draw to find the intersection points, right? In this case, clearly these two intersect, right? At the point, let's see. Intersection point. The intersection point is the order pair 2, 4. All right. What else? And so notice here in this case, we're looking to find the area inside this, right? The one that I'm highlighting. Well, not the area where we're going to evaluate the double integral over that region that I just highlighted. All right. Okay, so in this case, I'm going to do the same as I did it before. I'm going to integrate with respect y first and then with respect x. Okay, so we have the double integral, right? Double, x e to the y squared dy dx. All right. Now let's see what's going to happen here. Okay, so the limits of integration go from again, let's call this the lower, which is y equals x squared. And on the other hand, this is y equals 4, which is the upper. All right. Let's see. The limits of integration, so for the y's go from the lower, I am keeping the same colors, that goes from x to 4. And as far as the x's, in terms of x, we're going to go from x equals 0 to x equals 2. Okay, so that's the integral that we set up for this problem. Now, as usual, let me write down the big bracket and separate the innermost integral from the outermost one. All right. Okay, notice, let me highlight, as usual, let me highlight the integrand. And notice I'm highlighting the dy, which denotes that we are going to integrate with respect y. So that means I'm going to take that x outside of that innermost integral, right? In order to evaluate integral 0 to 2, all right? So bracket x times the integral of x, the integral that goes from x squared to 4 of the function e to the y squared dy. All right, that times dx. Okay, let me take this term right here, this one right here, the integral, everything I'm highlighting here. I'm going to look at this separately, all right? So this requires, right? This requires to evaluate the integral of e to the y squared dy, right? Okay, let me forget about the limits of integration. They don't matter here. Let me do a u substitution. U equals y squared du equals 2y dy. But notice something weird. In this case, we are missing, notice this factor of y, missing a factor of y. And again, keep in mind that when we do integration using substitution, we can always compensate, multiply by a number that provided you divide out another number, right? However, we cannot just add a y and then divide a y right here. That cannot be done, right? So because of this reason, we cannot evaluate this integral. So we can't evaluate this integral right here, unfortunately. So we're in some sort of a dead end here, right? So what can I do here? Just skip the problem, we're done. No solution? No, that is not a solution. There is an alternative to this problem. The alternative to this problem is to reverse the order of integration, right? Now, but the thing is, okay, let me highlight this in a nice way. Okay, I need a different color here. Okay, I'm gonna use this light blue. I'm gonna use this light blue. No, I need something contrasting. I'm gonna use this strong green. Okay. Reverse. Reverse the order of integration. Okay, so this is what we do. Reverse the order of integration. All right, but when we change the order of integration, this is the extra thing we do. Change the upper minus lower, change that upper minus lower for a rightmost minus leftmost. All right, so this is what we're going to do. All right. God. Okay, so let's look at this lower function right here. This will be turned into, if we take the square root on both sides, this is the same as x equals the square root of y. All right, and this will be now the rightmost, right? Let me put an arrow here. This will be the rightmost. Okay, and then this vertical line right here, right? I don't want to mess it up, right? This one right here, the y-axis rather, right? Come on. Okay, the vertical axis. This will be the leftmost. Okay, I need more space here. Let me see if I can drag this a little bit more. Leftmost, right? Rightmost minus leftmost, but that leftmost will be x equals 0. So we are going to take a different approach. On the other problems we did upper, right? We did upper, right, minus lower. In this case, we're going to take a different approach. We are going to twist this into the rightmost minus leftmost. All right, let's set up the integral that solves this problem. All right. So instead of writing x, the same integrand, I'm going to integrate with respect x first and then with respect y. All right, the lower limit with respect x will be, okay, the lower limit will be the rightmost, right? In this case, the rightmost will be the square root of y, and the leftmost will be, I'm going to use green here to highlight this, to 0, right? That's the square root of y, all right? And then what about the limits, the numerical limits for the y variable? For the y variable, we're going to go from the lower y to the upper y. In this case, we're going to go from 0 to 4. All right, 0 to 4. Okay, let me erase this. All right, now let's, as usual, integral from 0 to 4, big bracket, the integral from square root of y to 0 of x e to the y squared dx times dy. So now let's look at the integrand right here, x e to the y squared dx. Now in this case we're integrating with respect x, so the factor e to the y squared, which doesn't depend on x, I'm going to write it outside of the integral. Okay, so the integral from 0 to 4 of the quantity e to the y squared times the integral from square root of y to 0 of x dx times dy. Now let's look at the integral that we were left with here. We are only integrating with respect x. We're integrating x with respect x. The integral of x is x squared. All right. So this will be the integral from 0 to 4 of e to the y squared times x squared divided by 2, and in this case we're evaluating this quantity from x equals the square root of y to x equals 0. All right. So this will be the integral from 0 to 4 of e to the y squared, and I'm going to factor out the 2 as well, right, in the denominator. Okay, e to the y squared divided by 2, and quantity squared minus quantity squared, all right, times dy. So the first quantity squared will be the upper limit, which in this case is 0, and then the lower limit, which in this case is the square root of y. Notice when we square the square root of y, the square root symbol cancels with the square power, all right, because they're inverses to one another. And then we have 0 squared, which is going to be just a 0. All right. Okay, let's keep going here. Okay, let's keep going with this. Let's see. Hold on a second. Never mind. Did I get the wrong limits? Yes, I got the wrong limits, guys. So let me invert. At this point, let me just invert the limits. Okay, I'm going to erase all the limits of the first integral. Sorry about this. I did this upside down. I did it backwards. Okay, let me do upper, which is square root of y, and lower, which is 0. Okay, upper limit square root of y, or lower limit 0. Upper limit square root of y, lower limit 0. Over here, let me erase this as well. Yes, otherwise we're gonna get a totally different answer, right? It's a good moment to fix this. Okay, and okay, quantity squared, so this will be square root of y, and let me write this a little bit bigger so it's easier to read, by the way. All right, and 0 for the lower limit. Okay, so this second term is going to go to 0, and again the radical symbol will cancel the power of 2, leaving us with only, I'm going to take this 1/2 outside of the integral, right? Integral from 0 to 4 of e to the y squared times y minus 0. But what is y minus 0? Isn't that just y? So this is 1/2 times the integral of from 0 to 4 of e to the y squared. And notice the little space I'm going to leave here. This one right here. I'm going to leave that space for a reason. All right. So now we can evaluate this integral, right? As opposed to what we did above here, what we tried to evaluate. Notice we wanted to evaluate e to the y squared, right? E to the y squared with respect to y, but we were missing that power of y in order for that substitution to be able to do it, right? So in this case, we have that missing power or factor of y, right? And this is going to work out. U equals y squared du equals to y dy. All right, so we have the y dy, right? But we're missing the number 2, the factor of 2. You may add that factor of 2 provided you divide that out. Okay, so notice the few things that are going to happen. At the same time, I'm going to change the limits of integration. See what I'm going to do here. I'm going to do u of the lower limit, 0, and u of the upper limit, 4, right? So u of 0, essentially plug in 0 squared and plug in 4 squared. This is going to give us 0 squared is 0, 4 squared is 16. So we are going to have the following. Number 1, multiply this half with that 1/2, right? That's going to give us a 1/4 times the integral with the new limits. Again, what did we do? So we did a substitution to transfer, to basically go from the world of y to the world of u. However, if we carry a function to a new world, so we need to also transfer the original limits of integration from the world of y to their corresponding in the world of u, right? And then this is e to the u du, all right? So now we need to evaluate the integral of e to the u, which is itself, okay? Itself, e to the u, evaluate from 0 to 16. Okay, so let's do 1/4 times e to the 16, which is the upper limit, minus e to the 0, which is the lower limit. Now, what is e to the 0? Any quantity to the 0 is the same as 1. Okay, 1/4 times e to the 16 minus 1, and that's the final answer. Okay, that's the final answer to this problem. Finally, why is this a good problem? This is a good problem because you may run into situations like this in which you set up the integral, right? But at one point you feel like you are in a dead end, right? So if you get in some dead end, well, that's not the end of the problem. We have another alternative, right? The other alternative is to reverse the order of integration. The thing is, when you reverse the order of integration, when you have general regions, not just rectangular regions like we did on the first couple examples, we need to redefine the upper minus lower, right? Which is what I'm highlighting here. We reverse the upper minus lower for a rightmost minus leftmost, right? So we need to rewrite these equations, these functions that we're given for this region, right? And then we conduct the integration over the new integral using the new reversed order of integration, and this is what we get. All right. Okay, guys. So I believe this section is already a big section, right? So in a way, I'm going to skip the next couple of examples, which would be section 8.8. I think this is already good enough. The reason why I'm skipping is because what we're really doing here when evaluating the double integral, we are really finding the volume of a solid, right? I don't want to just keep doing everything of the same. And on top of that, I think the number of exercises that I'm planning for homework are going to be good enough, and some of them, as you can tell, take a page or a page and a half to solve, right? So I think this is good enough about multiple integrals. So the next chapter, by the way, I will be changing the order of the chapters. So the next chapter should have been differential equations. However, I would like to save differential equations for the end of the of the semester maybe. So I think I'm gonna do the next topic we're gonna do is trigonometry. So then the exam number 3 will be covering these double integrals and trigonometry. For now, this is the end of this lecture, right? And I will see you on the following video. All right, see you next time.